Hello. In this video I'm going to show you how to derive the electric potential for a charged line segment. And so what we're going to do is start off by drawing a picture of the line segment. I'm going to make it look like a tube, and we're going to spread out charges uniformly on that tube. The total charge is going to be plus Q, and it's spread out evenly. I'm going to make this problem a problem where we're going to focus on the line that bisects that line segment of charge. Okay, so this is the bisecting line, and we're going to try to figure out the voltage at point P, which would be right here, and point P is going to be a distance x away from that line. Okay, now I mentioned that this is a line segment. It's not infinite. It is not infinite. And so what we're going to do is say that the total line segment is going to have a length of 2a. So going from the origin up would be a distance a, and from the origin down is a distance of negative a. And so the total length here is 2a. Okay. So our goal is going to be to derive potential, or the voltage, as a function of x. And so we would expect to get a function that gets smaller as you get farther away from the line segment. Okay. Okay, so what we're going to do with this is we're going to have to integrate, and we're going to have to divide up this line segment into small pieces. Those are going to be the calculus small pieces that we divide the charge into. The location of a piece is going to be indicated with the variable y, because it's the vertical position of that piece. And this piece is going to be, of course, dq, which is the small piece of charge. And the width of that piece, right, which is very, very small, is going to be dy. And I'll put that in the picture as well. And so what we're going to do is we're going to look at the contribution of that piece to the potential at point P. So this piece is going to add a little bit of electric potential at point P. And of course we're going to have to add up all of the contributions of the different pieces, and that's where the integral comes in. Okay. Now, one thing I'm going to note here, this is important, I'll put a star by it, is when we do this integral, we don't need to worry about components, because electric potential is not a vector. So no components needed. And that's important, and it actually makes this problem easier. Okay? So the reason is because potential is a scalar. And you'll see that that's going to make our life a little bit easier. Okay? And so the way that we're going to solve this problem is we're going to basically say that the total potential is going to come from all of the individual contributions of these point charges. And so we're going to do an integral and we're basically just going to add up all the k, q over r terms in our integral. So do you recognize this? This term inside of here is the voltage for a point charge, except our point is going to be the dq now. Okay. So we're going to do that. Now we're going to do a couple of little substitutions here to help us. First of all, we're not going to use r. Instead, we're going to recognize that r by the Pythagorean theorem is x squared plus y squared square root. So we're going to substitute that for r. The second thing we're going to do is we're going to not use dq directly. And the reason is that as you move up and down this line and you pick different dq's, r is going to change. So we don't want, it's not going to be easy for us to use this variable. What we want to do is we want to do something that has a dy in it. And then we can let that go from negative a to a, and that would be much nicer. So to take care of that, I'm going to remind myself, I'll do this over here, that the charge density of this whole segment is the total charge over the total length, coulombs per meter. So Q over 2A, because 2A is the whole length. But if this rod is uniform, that must be equal to the charge density in a very small piece. Okay? So if you like, this is the global charge density across the whole object, and this is the local charge density in the small piece. And the reason we can say those are equal is because this is a uniform distribution of charge. So that's going to be the trick that allows us to get rid of dq, and we can now write dq is equal to q over 2a times dy, and that will be our substitution for dq. So let's do it. A couple more lines and we're done. We're going to factor out k here from the integral. On the top part, I'm going to replace dq with q over 2a times dy. As soon as I do that, I can now put endpoints on my integral. I can make it a definite integral. And then I can write in the denominator x squared plus y squared. So please, keep track of the different letters in here. We've got x, we have y, we have a. A is a fixed distance, and y is going to be the variable of integration, and x is going to be something essentially which is fixed because we're deciding it when we set up the problem. So we factor out a few more things here. We've got k times q over 2a times the integral dy, x squared plus y squared to the 1/2 from negative a to a. And at this point, you kind of might just have to stop, and because this integral is actually kind of tough to solve. All right, I'll put hard to solve. And in this class, at least, when we get to integrals like that are pretty tricky to solve, that would take a lot of other paper, side paper to use, we are just going to kind of cheat and use an integral table, which is okay. So people in physics do that all the time. And so if you look on your formula sheet, from the official formula sheet for the AP Physics C course, you will find this integral, and it's right there. The variables are kind of switched around, and so you're going to have to kind of play a little game here with these. If you check out the variables on here, this x is going to actually become y, because the variable of integration here is dx, but here it's dy. So wherever we see an x over here, we're going to have to replace it with a y. Also, if you see the a is actually going to be our x. And so wherever we see an a, we have to replace it with an x. And I know that's confusing, but it's just a little game that you play when you solve this, okay? So you need to probably practice with that, because the variables here don't always match your problem. So I'm going to go ahead and put this in here. I've got kq over 2a, brackets, and this ends up being times the natural log, and then of the following: y plus y squared plus x squared under the square root from positive a to negative a. Okay. Now you should verify that, make sure you can get that same expression. But that is the integral, and those are the endpoints. And so then, to finally get the final expression here, you would take this, substituting y's for your a's, and for the minus a's, and you would subtract. Okay. So I'm gonna cut right to the chase. I'm gonna get to the answer here, because you know that when you take the difference of these two endpoints, like subtracting, that kind of difference, that really becomes a quotient. That's something from the laws of math, right? So I'm just going to go right to that step, and I'm going to put the thing that I begin by subtracting, which is the plus a. Remember, it's final minus initial. So I'll have a plus a squared plus x squared on the top. And then when I would subtract the other part, that would put me down here on the denominator. So this is negative a plus a squared plus x squared, square root. And that is actually our answer. It is not pretty, and it probably would be helpful if you were to graph this. In fact, that might be a good thing to do. I would say maybe graph it in Desmos. But what you should see is that the potential, the v, is actually going to get smaller as x gets bigger, as you get further away from this line segment. Now, I know that's probably not the most satisfying thing in the world, and that's not a very it's not a very stringent test of the function, but at least it proves that it's reasonable. Okay. And I think with this particular function, I'm just going to leave it at that. This is a good exercise in just kind of setting up an integral when you have a charge distribution that's pretty easy to deal with, and starting off by integrating kq over r and just kind of working through and solving the integral, coming up with an expression. So this problem is really just an exercise for you in how to set up and solve for potential when you know the charge distribution. Okay. One last thing I'll say before I end is you might be wondering, well, is there an easier way to do this? And the answer is no. And the reason is because this line segment is not infinite. This line segment is finite. And so the electric field would be very difficult to deal with in a problem like this. So the electric field is probably going to be going in different directions near the ends of the wire. And that would make any type of integral with the electric field very difficult to do. So for that reason, we cannot use an electric field path integral on this. I know we haven't talked about those yet, but we will really soon. Okay? So anyway, make sure that you can do this, work through the steps on your own, and some good practice with how to use an integral table and substitute in. So graph it in Desmos, please, and then I think I gave you a problem to try out for your own. All right? And good luck.